Welcome back to the module on one-sample hypothesis tests. I am Ellen Gordon. In this video, we will go over another example of a one-sample z-test. If you refer to your prep assignment, we can read the research description. A company hopes to reduce the mean time required to process customer orders. Previously, this mean was 3.8 days with a standard deviation of 1.3. They study the procedure and eliminate some unnecessary steps in hopes to succeed in decreasing the average processing time. An analyst takes a sample of 30 orders that were completed using the new procedure. The data can be found in this sheet. Conduct a hypothesis test with an alpha of 0.01 to determine if the new procedure significantly reduces the average processing time in comparison to the previous procedure. Remember, the first step is to select the test, or to identify the appropriate statistical test. A lot of times it's easy to do that if you complete the descriptive statistics table. According to the research description, there was a sample of 30 orders that were completed using the new procedure. So the new procedure is our sample. So this sample data is the new procedure. So we can use Excel functions to determine those statistics. Remember, for the standard deviation function, we use .s because it's sample data. And for the sample size, we can use the count function. The previous processing mean was provided in the research description. The mean was 3.8 and the standard deviation was 1.3. And this is population information. Since it's a population, there is not a sample size, so we can type in NA. And typically all values are formatted to 2 decimal places with the exception of a sample size. So you can see that we are comparing two groups. We are comparing the new procedure average to the previous procedure's average. So we're comparing two group means. One group is sample data, and the other group, we know the population mean. So we're comparing one sample to a population mean, and we know the population standard deviation, so that would make it a one-sample z-test. There's a handout posted on ISMS that explains all the different steps of the hypothesis test. Again, the case depends on the research hypothesis. If it's hypothesized that the two groups or the two means are different, it's two-tailed. If it's hypothesized that the group of interest is less than the population mean, then it's a one-tailed left. If we're hypothesizing that the group of interest is greater than the population mean, then it's a one-tailed right. Again, the research hypothesis can be found in the research description. And you can see right here, we want to determine if the new procedure significantly reduces processing time in comparison to the previous procedure. So we are hypothesizing that the new procedure is going to be less than the previous procedure. So that would be a one-tailed left. The next step is the hypotheses. Again, the null hypothesis is the hypothesis of no significant difference. And the alternative hypothesis is our research hypothesis, which we just determined is we think that the new procedure is going to be less than the previous procedure. Here are the hypotheses and symbols. Again, we're conducting a one-tailed left. When indicating the hypotheses and symbols, I think it's the easiest to start with the research hypothesis, and that's that we think the new is less than the previous. And then the null hypothesis is just the opposite of that. So we would say that the null hypothesis is greater than or equal to. Remember, the null hypothesis always has an equal sign in it. The next step is to determine alpha. Again, alpha will be provided in the problem description or the research description. Sometimes it's referred to as the significance level. Sometimes it's denoted using this symbol. And alpha is either 1% or 5%. And you can see in our research description, we are working with an alpha of 1%. Alpha is the objective rule on when we will reject or when we will fail to reject the null hypothesis. Our alpha is 1%. That means that we'll reject the null hypothesis if there's a 1% chance we observe our sample mean if the null is true. So if the null is true, The new processing time is the same as the previous, which is 3.8 days. If we find or observe a sample mean that's in the bottom 1%, we will reject the null hypothesis and will accept the alternative that the new processing time is less than 3.8 days. If we don't, if our sample mean falls within this area, we'll fail to reject the null. In other words, we'll accept the null and we'll conclude that the new processing time is the same as the old. The next step is to compute the critical values. Again, the critical values are the z-scores that are associated with alpha. So we want to find the z-score that's associated with the bottom 1%. If you look here on the table, these are the functions for a one-tailed left test. The function for the lower limit is norm.s.inv, and then we click on alpha. That's what it's asking when it's asking for the probability. When it comes to a one-tailed left, there is not an upper limit. So what we can do is we can type in NA. So for a one-tailed left, there's only a lower critical value. There's not an upper critical value. In fact, the only type of test that has both the lower and the upper critical values is a two-tailed test. Here's a visual depiction of our critical value. So negative 2.33 is the z-score that's associated with the bottom 1%. Again, you can see that we have a lower critical value, but we do not have an upper critical value, and that's because we are conducting a one-tailed left. We think that the new processing time is less than the previous processing time. The next step is to compute the test statistic. Again, we already have computed the descriptive statistics, so now we can compute our test statistic. Here's the formula for the test statistic. The formula is the sample mean minus the population mean. So we have the sample mean, which is the new processing time, minus the population mean, which is the old processing time. And then we divide that by the population standard deviation divided by the square root of the sample size. And our test statistic is negative 1.54. Here's a visual depiction on where our test statistic falls on the standard normal distribution. The next step is to compute the p-value. The p-value is the percentage associated with our test statistic or our z-statistic. There's different functions for different types of tests. We're conducting a one-tailed left, so this is the function that we will use. The function is norm.s.dist, and then it asks for z, which is our test statistic, our z-score for the sample mean, and then for cumulative, we will type in true. I recommend formatting p-values as percentages, and we can show them to 2 decimal places. Here's a visual depiction of our p-value. Again, the p-value is the percentage associated with our test statistic. Our test statistic was negative 1.54, and 6.12% is to the left of our test statistic. Step 8 is to make a decision regarding the null hypothesis. So we need to determine if we're going to reject or fail to reject the null hypothesis. There's 2 approaches we can use, the p-value approach and the critical value approach. Both of these approaches will yield the same results, and they will always be in agreement. For the p-value approach, we compare our p-value to alpha. If our p-value is less than alpha, we reject. If our p-value is greater than alpha, then we fail to reject. Here's the visual depiction of our p-value approach. You can see that our p-value, 6.12%, is larger than alpha of 1%, so we are going to fail to reject the null hypothesis. For the critical value approach, we look to see if our test statistic falls in that rejection region. You can see that our test statistic of negative 1.54 does not fall in the rejection region. Again, the critical value marks off the rejection region. So if our test statistic falls farther out on the tail in comparison to our critical value, we'll reject. If it doesn't, we'll fail to reject. Again, you can see it does not fall in that rejection region, so we will fail to reject the null hypothesis. Here's a written description of the critical value approach. We are conducting a one-tailed left. If our z-statistic is less than the critical value, then we would reject. And our z-statistic was greater than the critical value. It was not less than, so that means we are going to fail to reject. So our decision is to fail to reject the null hypothesis. The last step is to write a conclusion. Anytime you fail to reject the null hypothesis, your conclusion is the null. If you fail to reject the null, that means you're accepting the null hypothesis. So our conclusion is going to be that there's not a significant difference between the group of interest, which was the new processing time, and the population mean, which was the previous processing time of 3.8 days. There is not a significant difference when comparing the new processing time and the previous processing time of 3.8 days. So basically what we found is the new procedure does not reduce the amount of time it takes to process and complete a customer's order. So in conclusion, what we did was we tested the null hypothesis that the new processing time was the same as the previous with a mean of 3.8 days. Our sample mean was not far out on the tail. It did not fall in the rejection area, so we failed to reject the null hypothesis, so we are accepting the null hypothesis. You can see that the sample mean for the new procedure was 3.43. Yes, this is less than 3.8, but what the test is telling us is that it's not a big enough difference to suggest that the population mean for the new processing time is different from 3.8. Again, we expect sample means to differ a little bit from the population mean. What the test is telling us is that this sample mean isn't that big of a difference from the population mean of 3.8, and it's not a big enough difference to conclude that the population mean is any different from 3.8.